Dear students, in this video we will talk about Baeyer-Villiger rearrangement. Baeyer-Villiger rearrangement is also known as Baeyer-Villiger oxidation. Because insertion of oxygen takes place. In this reaction, conversion of ketones into ester takes place, and here we can see oxygen has been inserted. So this is Baeyer-Villiger oxidation, and this reaction takes place in the presence of per acid or peroxy acid. Both are same. And if we use cyclic ketone in the presence of per acid, or we can call it peroxy acid, formation of cyclic esters takes place. So here is also we have insertion of oxygen. So cyclic esters are also known as lactones, and this reaction can also be used for the oxidation of aldehydes. In these reaction conditions, aldehydes are oxidized to corresponding carboxylic acids, or sometimes to formate esters. So this is formate ester and this is carboxylic acid. So it depends upon the relative migratory aptitude of R and H, which we will discuss later. Baeyer-Villiger rearrangement or oxidation was discovered by Adolf von Baeyer and Victor Villiger in 1899, and later in 1905 Adolf von Baeyer was awarded Nobel Prize upon his services in the field of organic chemistry. So now we see the mechanism of the reaction. Since we are using acid, so ketones would be protonated in the presence of acid H+, and because lone pairs are higher in energy, so lone pair would abstract the proton. This proton is coming from the per acid which we are using. So this, due to the presence of this extra oxygen, this is called per acid or peroxy acid. So in the first step, this would dissociate to give rise to this A9 plus H+, and this H+ would be taken up by the ketone and it would be protonated, and as a result we will get positive charge on oxygen. And we know that when in neutral state an atom loses or gives away its lone pair, it gets positive charge. So it gets positive charge, the oxygen, and when an electronegative atom gets a positive charge, it becomes more electronegative. Its tendency to pull electrons from the neighboring atom becomes greater, and as a result this becomes more electrophilic. So in the next step, this anion would attack here and we would get the addition and this intermediate is formed, and this intermediate is Kriege-like intermediate. And we have talked about it already, that when an sp3 carbon is attached to two or more electronegative atoms, it is unstable, so it would collapse. So this would come down, and one of these two groups would migrate to this oxygen. And if both the groups are same, then anyone could migrate, and if both are different, the migrating group would be the one which would be better electron donating. So this group would migrate here, and this bond would be broken, and as a result we would get this one plus RCOO negative, and proton, this would take the proton, and finally we will get aster and corresponding acid. So this is the mechanism of the Baeyer-Villiger oxidation. It is important to note that the bond breaking and migration takes place in one step, so this reaction is concerted. In a single step, the migration takes place as well as the bond is broken. So this is concerted reaction. I hope this is clear to you. Now we see some characteristics of this rearrangement. So in this rearrangement, migration towards electron deficient oxygen takes place. In pinacol-pinacolone rearrangement, we saw that the electron donating group migrated with its electron pair towards carbocation, and that was electron deficient. So in that case, carbon was electron deficient, and migration towards electron deficient carbon took place. And in this case, we have seen that the migrating group takes electron pair and migrates towards electron deficient oxygen. So in this case, migration towards electron deficient oxygen takes place. Second characteristic, the reaction is regioselective in nature. In regioselective reactions, one product is formed preferentially, and in this case the reaction is regioselective, and it depends on relative migratory aptitude of the migrating groups. And if we see the migratory aptitude, in general, tertiary alkyl is better electron donating and hence better migrating group than secondary alkyl, which is better than primary and which is better than methyl group. So this is the migratory aptitude. Next point is the migration takes place or migration occurs with retention of configuration. It means when Kriege intermediate is there, for example, this one. So when migration takes place, this comes here, and if, for example, this is chiral, and this migrates here, we will get this one. So stereochemistry at this center is same. So retention of configuration takes place during migration. Now different peroxy acids can be used. For example, MCPBA, metachloroperoxybenzoic acid. The structure is this one, and because chloro group is at meta position, so metachloroperoxybenzoic acid. Similarly, CF3, CO3H, trifluoroperoxyacetic acid. It's also trifluoroperoxyacetic acid, or CH3, CO3H, peracetic acid or peroxyacetic acid. Similarly, tertiary butyl hydrogen peroxide, TBHP, this one. So these were a few characteristics of Baeyer-Villiger rearrangement. In addition to that, these acids, we have Baeyer-Villiger monooxygenase enzyme. This is an enzyme which can also catalyze this rearrangement. So I hope this is clear to you. Now we see some examples of this rearrangement. Okay, for example, if we have this ketone and we subject it to Baeyer-Villiger oxidation, what would be the product? Here we have a small trick as well. We have to see two groups around this carbonyl group, and we have to compare between the two, and the group which is better electron donating would have oxygen inserted here at this position. So in this case we have methoxy group attached here in comparison to hydrogen attached there, and this is better electron donating, so therefore it would be attached with oxygen. So this is the product. And similarly, if we have acetophenone, this is acetyl group, here is phenyl, so it is called acetophenone, and among these two we have phenyl better electron donating, so this would migrate, and because it is migrating towards oxygen, so oxygen would be inserted here. So after Baeyer-Villiger oxidation, we will get this ester. Okay, now we see another example. In our next example, we can use a cyclic ketone. This is cyclopentanone, and in this case we have again both the substituents same, so this is symmetrical, and therefore any one of these could be migrated. So as a result we will get ring expansion and this electron would be formed. And if we have a compound, this one, if we treat it with MCPBA, what would happen? So I would like to ask you to complete it and try it by yourself, and we also solve it. Here we can see we have a peroxy acid, and here we have a ketone, here we have a double bond. So it means double bonds also react with peroxy acids. If you treat a double bond with MCPBA, in general we get epoxide, and this reaction is called Baeyer-Villiger reaction. Epoxidation of alkenes with MCPBA peroxy acid results in the formation of epoxide, and this reaction is called Baeyer-Villiger reaction. So we have two groups, one is double bond and here we have a ketone. So the product in the presence of this reaction would be here we will have epoxide and here we will get the ester. Now we have to see, this is cycloalkyl group, here is methyl group, and in general cycloalkyl has better electron donating ability as compared to simple alkyl. So oxygen would be inserted here and we would get this product. I hope this is clear to you. Now we see another example. If we have benzaldehyde and we subject it to Baeyer-Villiger oxidation, then there is possibility of insertion of oxygen at this position, and as a result we get benzoic acid. And similarly, if a reaction is done in the presence of 3-chloro-4-bromo-benzaldehyde in the presence of per acid, we get this benzoic acid as a product. And if we use this dimethoxybenzaldehyde, 3,4-dimethoxybenzaldehyde, because this is position 3, 4, 1, 2. So 3,4-dimethoxybenzaldehyde would result the insertion of oxygen here, because presence of two electron donating groups is making this group to migrate in Kriege intermediate. So as a result of Baeyer-Villiger oxidation, we will get major product resulting from the migration of this group. So this is formate ester. So I hope this is clear to you, and if you find any question or any confusion, you can leave your comments in comment box. Thanks.